All right, so everybody had their first experience of assignments and their tests. How'd they go? Good? You feel like that review lecture really kind of helped out, kind of summarize the two chapters? It really isn't that much physics, as like a lot of people are concerned when they hear MRI physics. It's really just kind of understanding the concepts. You might have a couple formulas here or there, but it's not hard math or hard physics. So don't ever think you can't do this class because of deep physics, in air quotations for people online. All right, so we are moving on to image weighting and contrast. We're really going to be focusing on our... You okay?
Sorry, I have a sharp pain in this.
So we are really going to be focusing today mainly on our contrast here. Next lecture, we're really going to be talking about our image weighting. So going back to X-ray, what does it mean to have image contrast? Or you could kind of define it in high versus low contrast. What does it mean to have high contrast in X-ray?
There's less shades of gray.
Less shades of gray, so more black and white, and a greater distance between those shades of gray, right? What does it mean to have low contrast? Many shades of gray, smaller distance between each shade. So typically with X-ray, where do you want to have high contrast, what body part, and where do you want to have low contrast?
High contrast for extremity.
High contrast for extremity, you want more black and white to see that bony trabeculation, right? And then low contrast, where do you want to see that? Abdomen, chest. Yeah, where you got the interstitial lung tissue, it'd be hard to see if it was burnt out. And then the abdomen tissue, where you have all different types of organs. So MRI is really no different when we're talking about image contrast, because we're really just talking about the different shades of gray or black or white, right? So we're able to differentiate one structure from another. That really gives us our contrast. When we were going to be talking about weighting next lecture, it's really how we adjust those parameters and what we call our extrinsic parameters on our MRI console to get a desired image weighting so that we can rule out certain things, like different pathologies. We can see anatomy better, or we can see, say, acute stroke with our diffusion-weighted imaging. We have different weightings to kind of visualize different things in MRI. So we have different weighted images here on the bottom of the screen. So we have a T2, a T1, stir, T2 star, flare, T1 post-GAD, and a diffusion-weighted image. So by the end of, I'd say, in the fall, you'll know how to create these images by adjusting your parameters. And you'll be able to identify these images on your MRI console, which will be very beneficial when you're in clinic. All right, so these are our objectives for today. So we're going to distinguish between those intrinsic and extrinsic parameters. We're going to review contrast mechanisms. We're going to talk about relaxation of different tissues. We're really going to focus on 3 different types of contrast, and then eventually we'll talk about their weighting, but we're going to be talking about T1, T2, and proton density. And then next unit we're going to be talking about partial saturation, what that means, and then we're going to be able to identify common images from MRI protocols. All right, so last year, we really talked about how we get basically our net magnetic vector that usually sits right here along B sub 0. What's B sub 0 stand for again? I think you had it right there. Go ahead. Go ahead. You're saying the static magnetic field. Yeah, B sub 0. And remember, that aligns with M sub Z, our longitudinal axis. But we talked about precession and resonance and that RF excitation pulse to get it down into the transverse plane. Because remember, our receiver coil that's sitting on the patient is 90 degrees from our static magnetic field, and that's where we receive our signal. So here, I'm just showing that we have 3 different net magnetic vectors that get flipped into the transverse plane, and if you have a larger net magnetic vector in the transverse plane, you're going to have higher signal. So I color-coded that as white. So anytime you have very high signal in MRI, you have white on your image. And then a little bit lower or smaller net magnetic vector, you get your grays. And then a smaller vector to absolutely no vector, you get black on your MRI image because you have no signal from those tissues in the transverse plane. So does everybody get how we can only get signal in the transverse plane? Remember, it's rotating around that transverse plane because we have to think about it in 3 dimensions. Due to precession, it's always going to be rotating. And every time it rotates past that receiver coil, it induces a voltage in that receiver coil that gets picked up by the computer. That signal's turned into, or basically it goes through our fast Fourier transform, just like an X-ray. That signal's creates our image. So let's quickly define image contrast versus image weighting. The difference in how the fat and water vectors recover and decay creates image contrast. All our tissues are going to recover and decay, or what we call relax, at different rates. And I always like to talk about fat and water just because usually they're on the opposite ends of the spectrum. Just because how the molecule is composed. So image contrast, just like in X-ray, is the difference between black and white on the image, or your grays. Second part of the lecture, when we talk about image weighting, is how we manipulate the sequence parameters that determines image weighting. So those are extrinsic parameters on our MRI console that we can change. You see all the MRI techs changing the TR, changing the TE, changing the next, changing the B value, changing your matrix. All these things can be manipulated, and those are our extrinsic parameters that give us our image weighting. All right, so we are divided into intrinsic and extrinsic. So going back to X-ray, what do you think are our extrinsic parameters that we can adjust in X-ray? What are your parameters on your X-ray console that we can adjust?
GBP, mass.
Okay, or just MA and mass, focal spot size. What else? What are some other things on that control panel? Yep, AEC. That could be something that you select, either the middle cell or the outside cells. Is there anything else? What's that?
The procedure. Which one you're doing?
Procedure? Yeah. So all those things that are things that we can manipulate. So those are going to be in the category for MRI over here called your extrinsic parameters. These are things that we can change. So you have your TR. So let's type out what these things mean. So I don't know why they flipped the letters, but TR stands for repetition time. Does anybody know what TE stands for? Any guesses?
Something echo.
Good. And then what's the T stand for, you think?
Time.
Exactly. Echo time. Flip angle we already talked about, right? What determines a flip angle? What were those 2 things that determined a flip angle?
The RF pulse.
I'm close.
The RF pulse, but how long it's on, and
Yeah.
the amplitude, not the frequency, because remember the frequency is always the same because it has to match what frequency? RF pulse has to match what?
Sessional.
The per sessional frequency, or the Larmor frequency. Yep. So we can just put here, just as a reminder, by determined by amplitude and duration of RF pulse. Okay, what do we think TI stands for? Just from your little observation rotations. I don't know if you guys ever talked about these things with the text. This one's called inversion time. This usually gives us our stir sequence, which stands for short tau inversion recovery, or our flare sequence. Anybody hear those words while you were in clinic? Yeah, stir and flare. Flare stands for fluid attenuating inversion recovery. FL is fluid, A is attenuating, IR inversion recovery. Stir, short tau inversion. Typically with our stir imaging, this is stir is going to basically suppress signal from and we'll go over this later on when we start to talk about pulse sequences, but just kind of a quick little synopsis of what a stir sequence does. It suppresses fat, applies an inversion pulse to all the tissues, and then it actually, the pulse sequence starts right as our fat recovers up to the transverse plane. So there's going to be no signal it's a very uniform fat suppression. Flare is a very uniform fluid suppression. And we usually do that on brain sequences when we're trying to rule out what we call white matter diseases or myelinating diseases like MS, where those MS lesions are right near the lateral ventricles, kind of near the corpus callosum. So we're able to visualize those a lot better when the fluid is completely black. Turbo factor, we'll talk about that, but it can also be considered what we call echo train length. So ETL stands for echo train length. And then our B value where we're talking about Browning's motion, and this is when we're talking about diffusion-weighted imaging. We change our B value to visualize diffusion of water, whether it's restricted or not. Diffusion-weighted imaging. So the higher the B value, the more sensitive our diffusion gradients are to water diffusion. But once again, you don't really need to know that for right now, but just kind of give you an idea of everything. So those are the things that we can change to get all these desired image contrasts. So you can see here how, just talking about some of these parameters, go back to our images here, we have a stir. Fat is suppressed. Flare, water in the lateral ventricles, or CSF, fluid, is suppressed. Diffusion-weighted imaging is a very fast echoplanar imaging. If we see a little bright spot right there, we would be able to determine that's restricted diffusion, and that could be considered an acute stroke. We have T2 and T1. We'll talk about that, and I don't think we have a proton density on there, but just to give you an idea of how we get the different weighted images. All right, so that we'll talk about next time and in the following units. But over here, we're really going to be talking about this today. Intrinsic contrast parameters. So these are things that cannot be changed, and they are inherent to the body's tissue. So the T1 recovery time of all the different tissues, fat, water, muscle, all those things recover at different times. The T2 decay times of all those tissues, they all decay at different times. The proton density. The proton density basically means how many hydrogen protons within a voxel. What's a voxel? Three-dimensional pixel. Exactly. You could just say 3D. Oh, that's not 3D pixel is a voxel. Flow. Our blood flow within our body, we cannot change. We can change our contrast parameters to make flowing blood bright on our images or make it look dark. But flow in general, or blood flow, we cannot change. And then our apparent diffusion coefficient. This is actually a calculation of how fast those water molecules are diffusing. So we can't change how fast things are diffusing within our tissues.
I'm sorry, what was flow again?
Flow, just blood flow.
Oh.
Blood flow. Or CSF flow. So I'll just type it down here. Let's say blood or CSF. Because we actually try and visualize CSF blood flow for certain pathologies. Does anybody know what a Chiari malformation is? Where the tonsils of the cerebellum kind of drop into the foramen magnum, cause kind of a little congestion. That backup could cause the CSF to not flow adequately. Sometimes that's what you'll need a shunt to kind of reroute some of that backed up CSF fluid. All right, so images obtain contrast through three concepts. T1 recovery, so right here is our T1 recovery curve. So know that a T1 recovery means our signal's regrowing. So anytime you see this line start to creep back up, that's recovery. That makes sense, right? The other way we obtain contrast is T2 decay. So our signal is decaying. And we'll talk about this more, but just in general, recovery curves look like this, and a T2 decay curve looks like this. Signal's going down for decay. It's going up for recovery. T1 and T2 relaxation depend on three things. The inherent energy of the tissue, how closely packed molecules are, and how well those hydrogen protons within that molecule match the Larmor frequency. So I did say that images are obtained contrast through three things. So here are the first two, T1 and T2, but the third one is proton density. And I've already kind of defined this on the other slide, but proton density is the number of mobile hydrogen protons per unit of volume, or voxel, of that tissue. So this is probably the most simple concept when we're talking about contrast, where we have a bright area versus a darker area. So you have high signal in areas if you have a voxel of tissue and then you have a lot of these hydrogen protons within that voxel. Because remember, all these little magnetic moments add up to create what? Little vectors add up to create what? The net magnetic vector. So think, this net magnetic vector over here is going to look a lot bigger, right? Than this one over here. It's only going to be this big. Because they have, in the low areas of proton density, you have less mobile hydrogen protons within that voxel. So a smaller net magnetic vector. Here we have more hydrogen protons per unit volume. So we get a higher net magnetic vector. So then you can equate this net magnetic vector is higher in signal. Because remember, it gets flipped into the transverse plane. So if it starts out with more, it's going to end up more in the 90-degree axis with more signal. Going back to that first slide where I showed you here, once it gets flipped into the transverse plane, see how this bigger vector will have more signal than this smaller vector here. All right, so now let's talk about the things that T1 and T2 relaxation depend on. So the first thing, inherent energy of the tissue. So anytime we're talking about inherent energy of the tissue, the main word we want to really kind of highlight is lattice. So lattice basically means the environment surrounding our mobile hydrogen proton. So lattice is the environment surrounding our hydrogen proton. So always equate lattice or spin lattice to T1 relaxation. T1 relaxation is also named spin lattice. So always relate the two. So T1 equals spin lattice. So if you see these interchangeable terms on a test, just know T1 relaxation equals spin lattice. So you have low inherent energy of the tissue when the molecular lattice is able to absorb energy from the hydrogen proton. So think of it like a sponge. So that lattice or the environment is the sponge, and these hydrogen protons are basically giving all their energy to the environment. You have a high inherent energy when the lattice can't absorb energy from the hydrogen proton. So think of it like a crappy paper towel. You know, the off-brand type, right? The one that you need the whole roll just to get, you know, clean up a spill of just water. So this is especially important with T1 relaxation because that relies on energy exchange with the lattice or the environment. All right, the next concept when we're talking about T1 and T2 relaxation is molecular packing. I think this one's kind of easy to understand. So closely spaced molecules, there's going to be a more efficient interaction between all those molecules. So think here we have 2 beakers of water, 2 beakers. Here we have water, or like CSF. Where those molecules are free-flowing. They don't interact as much as, say, if we had a beaker and then we just plopped a lump of fat in there. We just, you know, did a little liposuction and then just put it in that beaker. So those molecules are, you know, it's a solid. Those molecules aren't free-flowing, they're just right next to each other. So when they're closely spaced, as in fat, there's more efficient interaction. Spins interact with other spins more efficiently. And they give off energy to each other. If there's further space, there's less efficient interaction. And they're not going to come in contact with another spin. Because they might be floating around randomly. Every once in a while, they'll give energy to the other spin. So this is especially important when we're talking about T2 relaxation. And T2 relaxation can also be denoted as spin-spin. So make sure you write that down. T2 relaxation. Spin, spin. Where you're giving energy to your neighboring hydrogen nuclei. Those little magnetic moments are starting to interact. All right, our Larmor frequency. What's our equation? Here, what's the equation of Larmor? Larmor frequency or processional frequency equals, what are two other variables? Yeah, one's a constant. What's the constant? The number never changes.
42.
0.57. What does that stand for? What's that number? Megahertz per Tesla. Is that the static magnetic field or is that the gyromagnetic ratio?
Gyromagnetic
Exactly.
ratio.
That's the gyromagnetic ratio here, the Y or the lambda symbol. And then D sub 0 is our static magnetic field. So whatever we're scanning the patient on, 1 Tesla or 1.5. So that varies, right? So when the tumbling rate of, say, fat or water matches the Larmor equation or our Larmor frequency of hydrogen, there's a good exchange or an efficient exchange of energy. So remember, resonance, there has to be an efficient exchange of energy. It has to match the frequencies for these things to gain enough energy to oppose the static magnetic field.
When we say tumbling, does that just refer to the processional?
No, it's really just the molecule in general.
Oh.
So think, do you think fat or water has a higher tumbling rate? Basically how it turns over. Say if you have the two beakers, which molecule, because fat is divided up into a bunch of different molecules of fat, right? Which one do you think tumbles faster, fat or water? Just thinking about the makeup of it. Water. Water actually tumbles a lot faster due to its properties than fat. So, good question. Tumbling rate. So I would put down here water. Faster. Tumbling rate, which equals a higher precessional frequency. All right. Oops. I went back too many times. Let's see if I can do it. Just that water has a faster tumbling rate, higher. Lower precessional frequency. So in MRI, the book, and most places when you're trying to review for the registry, they always talk about the two extremes when it comes to contrast, our fat and our water. So we have a T1 weighted image here. Typically in a T1 weighted image, our fat is going to be bright because it recovers a lot faster than water. And our water is going to be darker, lower in signal because it recovers slower than fat. And just look at the composition of these molecules. Water is just H2O, right? It's a very small molecule. Where fat is usually composed of these long carbon chains. Might involve an oxygen, but a lot of hydrogens are linked to them. You can have saturated fats, unsaturated fats, but they're larger molecules. What's fat also called? Starts with L. Lipid. Okay, so let's talk about this concept of molecular binding, because that's going to help us kind of understand the tumbling and the precessional rates of fat and water. So Molecular binding is basically the way an atom shares its outer electrons will have a direct effect on the atom's magnetic susceptibility. Because remember, our hydrogen isotope, what's that called? Protein. And it's very magnetically susceptible because of its 1 proton and 0 neutrons. So it has a very, it has a positive charge to it, and that's what gives it that net spin, right? And that net spin creates a little bar magnet or dipole, and you could draw those with vector quantities. But that's what basically gives us our little magnetic moments. So we're going to talk about how water, in particular, pulls those electrons, or that 1 electron, away from hydrogen within the water molecule to make it seem more positive, right? And that positive feature is what makes it more magnetically susceptible. Compared to our lipids, where hydrogen is really just sharing that electron, and you don't really get a more positive or more negative side to that molecule. So here, molecular binding in fat. The hydrogen proton in fat is bound to carbon in large molecules called lipids. So that hydrogen proton keeps its outer electrons in fat. So you don't really get a more positive or a more negative side. But then we have water. So we have 2 hydrogen atoms arranged with 1 oxygen atom. So let's just draw that out. So going back to your first physics class with Don, how many electrons do we have around oxygen? In the first shell we have 2, but how many electrons in general? What's our atomic number of oxygen? 8, right? Okay, so let's think about it for a second. Okay, so for the first shell, we have 2, 1, 2. How many do we have in the next shell?
4.
Is it 4 or is it? What's our atomic number of oxygen?
8.
8. So 1, 2, 3, 4, 5, 6. Okay, so now we need 2 hydrogen. How many electrons does hydrogen have? Just 1, right? So to complete that outer shell, basically these hydrogen donate that 1 electron, right? So what happens with water molecule, usually this oxygen is very selfish. It's going to want to pull that electron away from the hydrogen. It don't really want to share it. It wants to kind of pull it away from the hydrogen. Still attached to the hydrogen, but it's just kind of pulling it so that one side of the hydrogen is going to be more positive and one side is going to be more negative. Which side of the hydrogen do you think is more positive?
That's up.
So I think I heard Lindsay say it up here.
That was me.
Oh, who said that? Jasmine. Awesome.
I need.
Gotta get credit when credit's due, right? So over here is the more positive end, and then down here is the more negative end. And then it's just the opposite for over here.